Okay, is it good? We've just finished lecture 1, which was the introduction to the course as well as memory in general. Now we're going to go into different topics, and this is the first topic that I'll start with, and I'll tell you why I'm starting with this one. We're going to cover many, many interesting things in memory. We're going to end at 5 today, but I'll be around if you want to ask questions. Feel free to ask questions. Yeah, these slides are also on the website, Roman tells you. Okay, so as I said, we're going to cover 4 key directions to begin with in this course, and we're going to start with security, reliability, safety. I'm going to tell you a story of why we start with this. Does anybody know about this person? Yes? Who is that? Maslow, because of the name, I guess. Yeah, there you go. Well, yes, I have a lot of side channels here. I should do better with these side channels. Okay, yeah, this is Abraham Maslow, and he was actually fascinated with why people do the things they do for good reason, and he actually dedicated his life to understanding that. I think he's more famous for this, basically the hierarchy of needs. Basically, he says that you need to have your very basic physiological and safety needs satisfied before you can talk about love, esteem, and highest forms of abstract art that you don't even understand. And that's exactly why we need to start with reliability and security, because if this is threatened, then a lot of the other things will fall. I'm going to deconstruct this later on, so take this with a grain of salt. Okay, does anybody know about this bridge? I heard something. The Tacoma, yeah, exactly, the Tacoma Narrows Bridge. If you've been to the Seattle area, that you would know this. It's over the Hood Canal, and it's not the exact same bridge, because this bridge was constructed in 1940, and this is what happened to it in 1940, 6 months later, because of aerostatic flutter. And later they reconstructed it and had a separate bridge next to it, so now it's more reliable. There are 2 bridges that are that are on the Tacoma Narrows. So fundamental reliability principles remain the same. One is going one way, the other is going another way. And I've crossed that bridge many, many times to go to the Olympic Peninsula from Seattle. But basically, this is an example of a reliability problem causing security issues and safety issues. In this case, people were lucky, I think, because there was only one little dog that died because it got stuck in a car. And the professor was trying to rescue it, wasn't able to rescue it. Well, but we'll see some other bridges later on that were not as lucky, maybe. I like this example because this is really what we're dealing in computers today also. These sort of reliability problems are affecting our safety and security. And it's going to affect more and more, maybe more importantly than these bridges going into the future, because computers are really everywhere in our lives. I like using this picture also. These folks who sit on top of Manhattan are very happy, but with a little fault on whatever they're sitting on, they could be quickly unhappy without even realizing that, right? So security, I think, is really about preventing unforeseen consequences. And this is one of the most general definition of security that I like using. And for this, I think we need a lot of infrastructure and patchability in the system. We're going to get back to that. I'm talking about this because I think this relates to what we have at hand also. I'll build up from the DRAM scaling problem, because we have reliability problems in the DRAM scaling, and that's affecting our security today. So I've shown you this picture before. DRAM is becoming increasingly less reliable because the size of the access device and the storage device are both reducing, and the fundamental properties that need to be maintained to keep it reliable are going away, essentially. And we already covered this, that's why I'm not spending time. Basically, as capacitor becomes smaller, it becomes less reliable. As access transistor becomes smaller, it becomes less reliable and more leaky. And we want to keep reducing it as far as possible. And as I said earlier, this has led to reliability problems. Basically, as we put more DRAM cells on a chip, the chip becomes denser, and the density of the chips that we employ in real production systems has a very strong correlation with the failure rates that we observe in real systems. And this is one of the papers that I would definitely recommend. There's a lot more analysis across all of Facebook's servers, actually. Facebook, at the time, in 2014 or so. And Facebook has a lot of servers. They didn't allow us to publish how much memory that we've actually tested and how many servers they have, because that apparently affects their stock price if it's published. And we have similar studies on flash memory failures also. But I find this fascinating. There's a lot more over here in this particular paper. And as I said, we also designed a bunch of low-level infrastructure, FPGA-based memory controllers. This is the first incarnation of that infrastructure to test these scaling issues with DRAM. At the time we started with the retention time issues. We wanted to understand the retention time of DRAM. And we also looked at latencies later. And I'm going to talk about RowHammer, which is something we discovered along the way. And we built this infrastructure also. And we later built this infrastructure where we did a lot of the RowHammer testing. And as I said, you could actually download this infrastructure and put it on the right FPGA, and you could do the studies for yourself if you would like to. And this is the paper that describes the infrastructure. And I'm going to skip this, but if you have this sort of infrastructure, you can actually examine what your retention time profiles on a real DRAM chip that exists looks like, right? And we actually verified that the real retention times look like this. We're going to get back to that. And we actually looked at the different parameters that affect the retention time of different cells in the DRAM chip. But while we were actually doing these studies, we actually also saw that one can predictably induce errors in most DRAM memory chips that you can buy in the field today. And this is the RowHammer problem. I'm going to talk about this, and we're going to use this as a springboard for other reliability issues that we may face into the future. What is RowHammer? It's essentially a simple hardware failure mechanism that can create a widespread system security vulnerability. And as I said, people are writing articles like this, popular articles, forget software hackers are exploiting physics. And I like this title because it actually gets to the heart of the problem. So what is the problem? As we discussed, a memory bank consists of multiple rows. And if you want to read something from the row, you need to activate that row, apply high voltage to that word line. And if you want to read something else, you need to pre-charge the array, basically, which applies low voltage to it. Now, if you keep doing this repeatedly, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, enough times before the cells get refreshed, it turns out in most modern DRAM memory chips, some of the adjacent bits in the adjacent rows flip, meaning they get corrupted. A 1 becomes a 0 or 0 becomes a 1, basically depending on how you encode things, charge gets lost. We call this the hammered row. This is basically you're hammering this row with a lot of activates, and we call these victim rows. As I said, you get these disturbance errors in adjacent rows in most real DRAM chips you can buy today. And what is most? Basically more than 80%. Regardless of the manufacturer, these are 3 different manufacturers, we saw that more than 80% of the chips exhibited this sort of errors. And this is actually a scaling problem. So why is it happening? Because cells are too close to each other, essentially. They're disturbing each other. There's not enough electrical isolation. Whenever you activate this row, you're actually affecting what's inside the other row. And one mechanism that induces this is electromagnetic coupling. So whenever you're activating this row, actually, let's go back here. Whenever you're activating this row, you're slightly activating this other row over here, which means that you're opening up this row very little. And if you do this enough times, you're opening this row very little, charge is leaking very little from the vulnerable cells over here. And if you do it enough times, you corrupt one or more of the vulnerable cells in the victim row because you've done too many of these hammerings that corrupt this row. This row doesn't get affected because, remember, you activate, sense amplifier amplifies it, and restores the charge. But this row gets affected because whenever you activate this, you're really not sensing this, amplifying it. You're just leaking charge out of it, very little. And if you do it enough times, you depleted the charge in some of the poor cells, vulnerable cells over there. So this is a scaling problem because things are too close to each other, and those electromagnetic coupling effects actually get exacerbated. And according to our results, this didn't get exposed to the outside world, meaning no chips that were manufactured before 2010 were affected. But the first occurrence is really in 2010. And later, all of the chips that we've tested that were manufactured between 2012 and 2013 exhibit this error. This is error rate per billion cells, and this is the time of manufacturing of the module, as you can see. And this is an industry-wide problem. It's really not a manufacturer-specific problem. Everybody saw the scaling issue earlier or later, depending on who's leading in terms of technology, as you can see. and they shall remain nameless over there, but you can guess who they are, right? These are DRAM manufacturers. There are not that many of them in the world, at least anymore. So, yes?
How do you check for this problem? How do you see it?
How do you see it? Basically, you keep activating a row. Activate, precharge, activate, precharge. I'm going to give you some examples. You can test it in an FPGA. In a FPGA-based memory controller, you can actually modify the memory controller and keep activate, precharge, activate, precharge, activate, precharge to the same row. But you can do it on a real system also, as I'm going to show.
That it will not be the row that will stay in the buffer, because you need every time to charge and recharge the row from the DRAM, no? As far as I understand, because the effect is in the neighborhood, probably. And when you always access the same row, you have the caching principle that the row will be in the buffer, in the open.
Yes. Yeah. You need to get rid of that basically. Yeah. I'm going to show you basically. You can do this on a real with real x86 code also, with real programs actually. And I'm going to show you. You need to bypass the caches. You need to bypass the row buffer. But if you're an FPGA-based memory controller, you can do anything you want actually, right? You basically activate, precharge, and that's how you do it. Yes. Flash certainly suffers from read disturb, but it's a different mechanism. If we have time, I'm going to talk about that. Emerging memory technologies suffer from some sort of read disturbance or write disturbance errors, certainly. Depends on the technology, certainly, but Flash has a very heavy suffering of read disturbance. But the mechanisms are a little bit different. But the difference in DRAM is DRAM gets directly exposed to the programming language. So you can actually corrupt your data structures very easily with this sort of error. Whereas Flash, there are a lot of mechanisms to prevent this, a lot of error correction. And most DRAM is not protected. It doesn't have error correction. OK, so why is this happening? As I said, DRAM cells are too close to each other. They're not electrically isolated from each other. Access to one cell affects the value of nearby cells due to electrical interference between the cells and between the wires that are used for accessing the cells. It's also called cell-to-cell coupling or cell-to-cell interference. I'm going to talk about that a little bit more later. So one example mechanism for the failure is when we activate apply high voltage to a row, an adjacent row gets slightly activated as well, and vulnerable cells in the slightly activated row lose a little bit of charge. And if you do it enough times, before the cells get refreshed, charge in such cells get drained. If you actually increase the refresh rate, this vulnerability reduces, because even though you're depleting charge little by little, if you frequently refresh, you refresh the cells, right? But that's not good, because refresh is not good in general, right? You don't want to increase the refresh rate as much. So that one solution is going to be refreshing more. So higher level implications, the simple circuit level parallel mechanism actually has enormous implication on upper layers of the transformation hierarchy, and that's what we're going to talk about in a little bit. Why? Because you can actually induce these errors with a user level program that looks like this. You could actually get rid of the mfence over here. That's basically fencing the memory operations. But basically, what this program that you could download over here does is it selects addresses x and y. Maybe it doesn't do a very good job in all systems, but selects addresses x and y, and it basically ensures that you avoid cache hits by flushing x from the cache, and you avoid row hits to x by reading y in another row, and you also flush y as well. Basically, what it does is ping pongs accesses to x and y enough times, hopefully, to induce errors if a chip is vulnerable. Very simple code, as you can see, right? So we published this code with the paper that I'm going to mention. But I think a better Google Project Zero improved this code. They basically realized that x and y don't need to be apart from each other. They can sandwich a single row, right? They call this double-sided row hammering. You select x and y such that you sandwich a single row in between. As a result, you get many, many more errors in between. OK, so this is actually a real problem. As long as you have a memory controller that's fast enough to access memory, you get errors. So it turns out Intel's memory controller were faster in this case. For whatever reason, AMDs were slower, but there's nothing special about Intel and AMD. As long as your memory controller is good, you exercise these errors. All of the memory controllers that are out there are able to do this. Even very slow FPGA-based memory controllers are able to do this, actually. So it's a real reliability and security issue. And I'm going to talk about the security implications of it. So when we actually first wrote the paper, this is going to be one of the required readings that we will put up, because it's fun to read it, I think. We said memory isolation is a key property of a reliable and secure computing system. and access to one memory address should not have unintended side effects on data stored in other addresses. And I think this is very fundamental for reliability and security. And we said that you could actually take over the system by exploiting these bit flips and hijack the entire system. And while we were actually looking at it, these good folks from Google Project Zero published a blog post that essentially did that. They did beautiful security engineering, and they exploited what they called the RowHammer bug. I like calling it a failure mechanism, to gain kernel privileges with user-level processes. And this is a copy-paste directly from Google's blog post. If you're really interested, I would definitely recommend it if you're interested in hardware security. This is a beautiful hardware security engineering. And I copied and pasted everything over here. They said they learned about the problem from our work. They tested a selection of the laptops and found that a subset of them exhibited the problem. And they built actually 2 working privilege escalation exploits that use this effect. One is not that interesting to me. It basically takes over Google's native client, essentially a virtual machine with a user-level program. But the other is very interesting. It basically exploits these bit flips to gain kernel privileges on x86-64 Linux. And the way they did that, you should read the details, but at the high level, on a machine that's vulnerable to the RowHammer problem, they were able to induce bit flips in the page table entries of a program where the page table entries actually pointed to the page table of the same program. Which means that if you flip the right bits in your page table entries that point to your own page table, that enables permissions to your own page table, let's say you can flip the right enable bit for that page table. Now you can actually gain write access to your own page table. Once you gain write access to your own page table, you can do anything to the memory. You can actually enable any kind of access to any part of the physical memory that you have. And at that point, the system is compromised. You just need to flip the right bit. That's it. Of course, it's not as easy to do that flipping. It requires a lot of spraying of the memory with page tables, opening up a bunch of files so that you can actually have a lot of, you can increase the probability of the attack. And if you're really interested in this, you can read the blog post that I point to over here. Yeah, that's essentially what they said. This is actually, it was able to use this to gain write access to its own page table and hence gain read-write access to all of physical memory. And later, people developed a lot of other attacks, which I'm going to cover. But people also start drawing pictures like this. This is the end of memory. I like this picture. It's very nice. I like these intuitive explanations. I think one person really nailed the problem by saying, it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations or perturbations open the door that you were really after. So if you want to break out of this room for whatever reason, if it's locked, you may want to start banging on the walls and hope that RowHammer effect magically opens the door that you're after. Okay. It's that?
Like an escape room.
Yeah, like an escape room. Yeah, sure. So there are a bunch of selected regions. I'm not going to cover this, but this is part of a talk that I normally give about RowHammer, and this is kind of the lecture that we're doing right now. But you can, these are the links. Google introduced this double-sided RowHammer, and then later there are a bunch of papers that I'm going to briefly talk about later on. But you can study these slides on your own. And these keep appearing right now. You can see that these are at top security conferences over here. This is one of my favorites. I'm going to talk about that in a little bit.
So with Google,
Yes.
when they broke into the Intel Linux kernel, that is a generic thing that can do it on any chip, or was on one specific chip?
Well, they did it on a bunch of laptops, basically. It wasn't on a specific chip. It's not on any chip. Basically, the memory chip needs to be vulnerable. And the memory controller needs to be fast enough, but everybody I think there's a lot of evidence out there that all of the memory controllers that we have are capable of doing this hammering enough times before the refresh.
Specific, I mean, do you have to get lucky, or is it something methodological that in the end will break it if you do it long enough?
Well, I think if you do it long enough, you'll break it, yes. The attack itself is probabilistic, so if you have limited amount of time, you may not be able to get lucky, but if you do it long enough, as you specified it, you will eventually gain.
On any DRAM chip?
Not on any DRAM chip, no. The DRAM chip needs to be vulnerable.
But you said 80% of them are.
Exactly, yeah, that's right. According to our results, it's 80%, that's right. So most of them are, I believe. But there needs to be more studies, I think, for the current DRAM chips
But
also.
this problem has not been solved.
Why study rather than correct it? You can easily have a form of cache in the controller that prevents like an inverse cache. Doesn't allow you to hammer many times on the same.
Yeah, we're going to talk about the solutions. Yeah, I think going forward, maybe that's one of the solutions, but what happens to all of the chips that are in the field? So you need to have some other solution for that. But I agree with you. I think solution space is very important. But we're going to talk about that. Okay, so these are interesting papers. So these are more recent papers, as you can see. Okay, this is one example paper. This is from 2016. Folks at TU Graz. Actually, these are the folks that got fascinated with hardware security after the RowHammer, and then they went on and discovered the Meltdown Inspector along with Google Project Zero as well. But basically, they showed that you could actually gain access to a remote server by exploiting RowHammer through JavaScript. This is really interesting, I think. And you can read the paper for more detail. This is folks at Vrije University in Amsterdam. They also showed that, this is actually very interesting, they showed that you could actually do this on ARM chips as well. People were somehow, I don't know why, they didn't think that it was possible in ARM memory controllers, but it's possible in ARM memory controllers also. And they exploited the deterministic memory allocation patterns of the Android operating system. They basically knew how the Android operating system allocated pages. They figured out vulnerable pages through profiling over time, to vulnerable pages to RowHammer, and they fooled the operating system to allocate the page table of this process into a location, into a page that they knew was vulnerable to RowHammer. And they were able to do this deterministically because they were able to fool the operating system, the system deterministic algorithm to allocate pages by doing appropriate page allocations. And as a result, they were able to actually gain control of many phones. And I believe they have an app that you can download if you have an Android phone and test if your system is vulnerable. You can find the app probably by searching for DRAMmer. Yeah. And more recently, people actually showed that you could do these attacks much more powerfully by exploiting a GPU, because GPU can access things much faster. And in a mobile system, you could actually, through the WebGL interface, you could actually use the GPU to do RowHammering much faster and take over the system. And you could actually do it over the network through the RDMA, remote DMA. These are more recent works from May, as you can see over here. And multiple groups actually did that. So these were concurrent papers that talked about through network request, RDMA protocol. And there's more to do, and people are very creative, I think, with these things. And maybe this is one solution. Maybe this is not the solution that you want, of course. Okay, so before we go into the solutions, I think it's good to understand things a little bit. So I'm going to talk about understanding RowHammer. There's a lot of interesting security research, and I think this is not the end of it. Well, hopefully this is the end of it if you actually get rid of your computer. But I think this is not the end of it. That people are very creative, and they're going to exploit this bit flip more and more. It was known before that if you actually flipped a bit, you could take over a virtual machine. There's a paper in IEEE Security and Privacy in 2003 or so from Princeton that showed, and they were able to induce bit flips in real memory by going to memory and heating it up. And that was the mechanism to induce errors, but that required physical access to memory. RowHammer doesn't require physical access to memory. Basically, based on the access pattern, you can actually induce a bit flip in a deterministic way. And as a result, you could take over the system. That's why it's very important for security. But let's understand at the very low level, why is this happening? I'm not going to go into a lot on why is this happening, but there are multiple reasons for it. Electromagnetic coupling, I discussed it. But sometimes conductor bridges get formed between the different parts of DRAM. As a result, charge leaks very quickly. And sometimes DRAM cells were shown to get permanently damaged because of hot carrier injection, and RowHammer actually can cause some of these effects as well. And it's not fully documented exactly what causes RowHammer in the literature, but it's really a combination of these effects, and this is confirmed to us by at least one manufacturer, actually two now, that want to remain nameless at this point. But actually, manufacturers are more reasonable about this. For a while, they didn't really want to talk about the problem, but I think more recently, I've seen a lot of talks from Samsung, for example, calling it the nosy neighbor problem. They think the one row is nosy to the other one. So it's good that I think people are more open about it. Okay, so we built this experimental testing infrastructure to study other effects, but we actually were able to look at RowHammer. So let's take a look at some of the studies that we've done. These are some of the characterization results. I'm not going to go over all of this. This is one example result. Basically, how close is the aggressor to the victim? The hammered row versus the victim rows. What is the address difference between them? This is the logical address that you provide to the DRAM chip, which may not be the internal address inside the DRAM chip. So most of these are different chips from different manufacturers, and these are the worst chips where we examine the errors. As you can see, most of the victims and aggressor are by one row address apart from each other. So they're adjacent in the address space. That's a lot, actually. In the blue chip over here, 100% almost. Some of the other ones, there's a distribution. As you can see, these are the adjacent ones. These are the non-adjacent ones. So some of them are far away from each other. This is true, at least in the logical address space. Internally, we don't know what's happening in DRAM because DRAM manufacturers can route things in a different way. So one of the explanations is that the non-adjacent ones could be really physically adjacent internally. We don't know. Or they could be because of rows that are remapped to some other place in the physical location in the DRAM chip, because some of them may be faulty, or because of whatever reason that the DRAM manufacturer uses to scramble the address bits. But most of them are adjacent, as you can see over here in the chips that we've tested. Okay. So, no, adjacent in terms of the address space, which is likely that it's adjacent in terms of physically, yes. But we've also seen that you can affect rows that are farther away from you. The effect reduces exponentially, but rows that are farther, you can basically affect multiple rows by having a single row. Mm-hmm. Yeah. Okay, so this is access interval, basically how fast you're accessing the victim or aggressor, right? Are you doing it every 50 nanoseconds versus every 500 nanoseconds? Clearly, if you're increasing your access interval, your hammering effect goes down because at some point things get refreshed. So you expect a curve that looks like this. So these are the errors, error rates. This is not allowed in the chips that we've tested. The TRC delay is about 55 nanoseconds over here, actually 52.5 nanoseconds over here. So as you increase the access interval, errors start reducing, and at some point they go to 0. So if you want to get rid of all of the errors, this is one method, not necessarily a great method. Increase the access interval to consecutive accesses to the same row up to 500 nanoseconds. Yeah, it gets rid of all of the errors that we've seen if you do that. But that's, of course, not a good solution because you may actually need that row because you may actually have a bad conflict that requires, or you actually have some locality in the row and you want to open it again. So bank conflicts actually require you to access the same row over and over. So if you actually increase your access interval, that's not a good solution in general. Yes?
Try keeping the access interval small, but limiting the number of accesses, just to make sure that it's the number of accesses within the refresh interval as opposed to something else.
Yes, yes, we've also looked at that. I don't have the results over here, but that clearly gets rid of the RowHammer also. But you need to know exactly how many accesses you need to limit it to. And that's dependent. But yes, that's one solution, certainly. Yes, limiting the number of accesses to given rows. So refresh is another one, examining the refresh interval. Today, we refresh everything every 64 milliseconds. If you do it more frequently, you expect the errors to reduce. If you do it less frequently, you expect the errors to increase. And that's exactly what you get. Basically, if you want to get rid of all of the errors in the system, you want to increase the refresh interval by 7x. Or increase the refresh rate by 7x, reduce the refresh interval by 7x. Not a good solution also, right? I don't think so. But clearly this is obvious because this is very similar to what you said. You do the opposite. You increase the refresh rate as opposed to reducing the number of accesses. And this is actually what's employed in many systems because it's the easiest thing to do. And this is the configurability that we have in existing memory controllers. Maybe there's more configurability that's not exposed necessarily, but this is the easiest thing that's configurable. Okay, data pattern. This is actually very interesting because this is a sign of electromagnetic coupling. So if you have this sort of solid data pattern, everything is the same, you don't get as many errors if things are different. So you get more errors over here, an order of magnitude more, because this increases the coupling. The voltage here is low, the voltage here is high. As a result, you get much bigger capacitive coupling between the rows. As a result, the probability of you inducing the errors becomes higher. Yes?
Trying to see what happens if you have, let's say, half ones, half zeros, but ones adjacent to zeros and zeros adjacent to ones.
So we looked at a lot of different patterns, but we couldn't find the, and this is actually a really interesting exploration. What is the worst case pattern? I think this was one of the worst case patterns, but we cannot claim that this is the worst case pattern. There could be other worst case patterns depending on how the DRAM is laid out and how, like what is the encoding that's employed internally also. Yes?
What could you say about the locality of the conflict? Is it the first neighbor, second neighbor, third neighbor?
Yeah, well, as far as we know, the biggest effect is to the first neighbor.
But is there an effect on the second one?
Yeah, there's an effect on the second one also. I'll show you in one sentence in one of the next slides. So you can actually affect more than one neighbor.
Okay.
It's a much smaller effect. Usually you affect one neighbor, but there are cases where you affect more than one neighbor. And it may be possible that as things get closer, that effect increases.
Because maybe the simplest solution would be to use just half of the rows.
Yeah, yeah, that's also proposed, but that gets rid of a lot of capacity, right?
Wouldn't ECC take care of that anyway?
ECC, that's one of the potential solutions that we will talk about.
All right.
So you get more than 1-bit error, sometimes 4-bit errors that we've seen. ECC actually gets rid of a lot of the errors.
I mean, just randomize the bits. I mean, you think you're writing the pattern, and then somebody comes and just scrambles it on the way. So there's no pattern.
Oh, there's no pattern. Yeah, I think, so randomization, of course.
Yeah.
But people have shown it. Actually, that scrambling is employed in many chips, but people have shown it existing chips are already also vulnerable. Maybe it's not vulnerable in the worst pattern. Yeah, maybe it's not in the worst pattern, but they're vulnerable. So if you actually somehow find the worst pattern, and if you're able to control it, maybe you can do more.
What is the bias between the zeros and the ones?
Say it again?
The bias of flipping a 0 to 1 and a 1 to 0.
Oh, that's a great question. Basically, in many cases, we saw flipping from 1 to 0, but there are some cases where you actually flip from 0 to 1. We think that it's because of the encoding. Sometimes 0 is encoded as charged. Sometimes 1 is encoded as charged.
It's because of the pre-charge. The pre-charge is not done halfway.
So it's because the phenomenon is usually because you go from charge state to discharge state. And 1 is encoded as charge state in many cases.
It's not VDD necessarily.
Say it again?
The pre-charge voltage is not necessarily your power supply.
It's VDD over
Yeah, it's VDT over 2. Yeah.
No, it's not. It's not.
DRAM, it has to be.
It's not.
It's some reference voltage, basically. It doesn't, maybe it's not necessarily that, but depending on the sense amplifier design, of course. But it's something, some reference voltage. But this is not related to pre-charge, right? This is related to charge loss in the end. Basically, if you do this enough times, you deplete enough charge, and you get rid of the charge. So if 1 is encoded as charge state, you'll go to 0 at some point. If 0 is encoded as charge state, you go to 1 at some point. So it really depends on the encoding. But in most cases, the paper actually has the data. In most cases, we saw 1 to 0 errors.
But what is the bias on the same chip?
So yeah, that I don't remember. I mean, there's a lot of data that we collected. Well, I can try to find out exactly. Okay. Okay, so there are a bunch of other results. So victim cells turned out they're not the same as the weak cells. Weak cell meaning they're leaky cells. It's cells that have retention, that cannot retain data for long. Because this is a different failure mechanism. So it turns out charge leakage from a cell, the retention time failure mechanism is different from RowHammer failure mechanism. There's almost no overlap between them. There's some overlap, but very little.
In that case, you try to see whether it's reciprocal. In other words, if cell A can damage cell B, can hammering B damage A?
Yeah.
For example, the wall between the clothes or something,
Uh-huh.
then it should work both ways.
It depends on the vulnerability of cell B, right? Cell A may be vulnerable, but cell B may not be vulnerable.
No, I'm saying if A is vulnerable to B,
Mhm.
because they're close together, let's
Yes.
say, not because of property of A,
Uh-huh.
but because they're somehow close together, something
Sure.
then B is likely to be vulnerable to A
Uh-huh.
as well.
Yeah, that's possible, sure.
Therefore, the lack of relationship between that and the cell itself being weak.
Uh-huh.
The cell being weak is a property of the cell.
I think there are different weaknesses. Yeah.
It should be reciprocal.
So we don't see that reciprocalness as much because weakness in terms of retention time is different from weakness for RowHammer, right? But yes, I agree that study needs to be done more. There needs to be more study over there. errors are also not strongly affected by temperature. This also, I think, supports this a little bit because retention errors are actually strongly affected by temperature. Charge leaks faster at high temperatures, but in this case, the failure mechanism is different. So this is very important. Errors are actually repeatable. Basically, if you are able to flip a bit, you're able to flip it again and again and again and again, and that causes a security problem. If this was more random, then you would have much less of a security problem. This repeatability is the problem. Because the cell is vulnerable, you can actually attack it.
It's repeatable even between different chips. If the same manufacturer creates two chips, the same bit in every chip.
You guys are asking very good questions. That's not necessarily true. No, it's very specific to the chip. So you'll need to profile the chip. But there needs to be, again, more study over here. Maybe there's some template that you can generate. And maybe there's some correlation. We didn't do that. That study is not easy to do because you need to test a lot of chips and you need to cross-correlate between them. And we didn't do that study. But as far as we know, it's not as repeatable across different chips because people tried out, some of the security folks actually tried out, okay, we have these errors in this chip. Now let's actually assume that they also happen in this chip, but they were not able to do that. Because part of the error mechanism is related to the manufacturing process. And the manufacturing process leads to these failures. And manufacturing process is very different for each chip. There's no perfect manufacturing. Okay, this was the question on ECC. Basically, simple ECC cannot prevent all errors because we see as many as 4 errors per cache line. And ECC error correcting codes are actually one solution to problems like this, but I will argue later that it's not a good solution because error correcting codes are very good at correcting stuff that you don't know how they happen. It's an overkill for things that you know how they happen. In this case, you know exactly why this happens. You have an access pattern. And if you actually identify that access pattern, for example, then maybe you can solve it. Or maybe you don't identify it, but you're more probabilistic, as I will discuss in a little bit. So this is the number of cells that are affected by the hammered row. As you can see, there are as many as 9 rows that are affected by the victim, by the aggressor. And you can affect many, many cells also. And we observed this, but we didn't exploit it. The folks at Google actually took our observation and exploited it. Basically, cells are affected by 2 aggressors on either side. And as a result, you can do this double-sided row hammering. OK, and this is the paper that maybe you can review. Maybe we can put this up for review, actually, for sure. Because this raised a lot of questions. Apparently, people are interested in this. Is that good? Yes. OK, yes, I heard yes. Okay, and this is another paper actually that I wrote recently that talks about like some of the other issues that we may face in the future. I'm going to talk about this later in this talk. Now let's go into solutions. Now that we've understood the problem a little bit, I think there's more to understand clearly. So some potential solutions. We cover this in the paper also. Make better DRAM chips. Good luck. Because that's but this is actually a potential solution, right? Maybe you use better isolating material, different types of transistors, different types of capacitors. Sure, that's all good, but it's not easy. Usually those things are costly if you want to do that. Refresh frequently, we're going to cover this more clearly. Refreshing more frequently would help. But if you do it across the board for the entire chip, that's an overkill because we want to actually get rid of refresh as much as possible. That's a scaling problem. Sophisticated ECC. Again, as I said, this is a very error correcting codes are very good at correcting random errors that you don't know how they appear. If your error failure mechanism is very well known, you can actually design a much more customized mechanism. And access counters, basically, in DRAM, keep some access counters and limit accesses. I think this is actually more specific to this problem, but how to do this efficiently becomes a problem. So I'm going to talk about a solution that's better, hopefully. But I think this needs to be investigated even more. There's potential here. But if you actually do it blindly, the area cost that you may have may not be very easy to handle. So among all of this may be the most interesting one. But I'll talk about some of the more interesting ones. OK, let's skip these because I already said this. So what is done in the field today? This is a security release from Apple. And I like using this because Apple was nice enough to credit our paper also over here. They basically said that they increase the memory refresh rates. And this is actually, in my opinion, the most reasonable solution that's out there in the field today. Other people have proposed software-based solutions, for example. Look at performance counters and figure out if row hammering is happening. And then once you figure it out, limit access rates. I think those are very intrusive. This is also intrusive in a different way, but this is very easy to employ, right? If your memory controller has this configurability, and most memory controllers have the configurability to change the memory refresh rates, you can actually reduce the vulnerability. They didn't tell by how much. They're probably limited by, maybe this doesn't get rid of all of the errors also, right? We don't know.
Is this the thing that drains the batteries on the iPhone?
No, maybe they have a different plan for that. I don't know. It might be, I don't know. But this is actually not good. As you mentioned, this is not a good solution because it's across the board. We want to get rid of refresh as opposed to increasing refresh. But this is actually an industry-wide solution for chips that are out in the field today. So our solution, of course, there are other solutions that I'm not going to cover, like this TRR mechanism that people have, which may or may not work very well. And are the chips going into the field vulnerable into the future? That's a very good question also. But I'll talk about our solution, which is customized for this mechanism. You can customize it even more. This was probabilistic. Basically, the idea is very simple. After you close a row, when you do a pre-charge, activate one or both of the neighbors with very low probability. Let's say 5 out of 1,000 times. It doesn't need to be even random. And this gives you a reliability guarantee that's better than hard disks today, if you choose P like this. And if you're not comfortable, you can increase the value of P. If you're comfortable, you can reduce the value of P. This has very little overhead. As you can see, for the workloads that we evaluated, the overhead is very little. The slowdown maximum overhead is very little. And it's also stateless. You don't need any state for this. Well, any state other than the counter for the probability, of course. But you don't need to have access counters. It's low complexity. And I believe it's a good solution. And there needs to be more to be employed here. So you can actually implement this in the DRAM chip or the memory controller. And I believe a form of this is implemented in DRAM chips, although maybe it's not implemented in exactly the way we proposed. There are reports that DDR4 chips are also vulnerable. We haven't tested them, so I don't know. But basically, in DRAM chips, you have enough slack and timing parameters, meaning whenever you're pre-charging a row, you can sneak in a refresh to adjacent rows if you have that slack in the timing parameters. And if you do that, you've essentially, you can actually implement para. And we've shown that there's a lot of slack. We're going to cover some of these papers later on. And because of that slack, you can actually reduce the latencies. So now, is this a good solution? We want to actually get rid of slack for reducing the latency. If you get rid of that slack, then you cannot actually do this in the DRAM chip that easily. I think the solution is better if it's implemented in the memory controller and the DRAM chip cooperates with the memory controller. Basically, if you implement in the memory controller, you should know which rows are physically adjacent. You can guess most of the time, maybe, but if you cannot guess, you're vulnerable in the worst case. So if the memory controller, if the DRAM chip cooperates and tells the memory controller, oh, this is my address mapping, you can use this address mapping to do this probabilistic refresh, then I think this is a good solution. But this requires a little bit more cooperation between the memory controller and the DRAM.
If you hammer the same address, why would you ever close the row?
Well, in order to be able to do the hammering, you need to close. So you cannot just do activate. You need to activate pre-charge, activate pre-charge. So every pre-charge, yeah. Because hammering doesn't happen in the row buffer. You really need to activate pre-charge, yes. The least you can do is activate pre-charge, activate pre-charge, activate pre-charge. But of course, in real programs, you cannot do just activate pre-charge. You need to do activate, read, pre-charge. Otherwise, the memory controller gets rid of all of that, right?
Another question. Don't you have to be in the same page to do damage with the victim?
What do you mean same page? No, these are completely different pages. So no, victim can be in a different. Victim has to be in a different physical row, but that could belong to a different application. So those are actually different pages.
The operating system would waste pages of completely different applications.
Yeah, absolutely, absolutely. It could be random. It could be belonging to the operating system. It could be belonging to any application. So you could be causing corruption to some other application, even if you're not taking over the system.
So the smart thing behind this is somehow to hit this place next to the very important victim.
Exactly. That's the idea. That's what those DRAMmer folks did with the Android operating system. They actually fooled the operating system to allocate a page to a location that they knew was vulnerable, and they hammered that location. And they were actually really deterministically able to take over the system, any Android system, with that operating system. Yes?
The random
So no, it's not real actually. It doesn't need to be random also.
Yes, it does, because if it's predictable, then the attacker can predict it.
Not necessarily, right? If you do it enough times, you cannot. The attacker has no choice, right?
No, like you can know when you're gonna do that and read from a different row, then you won't pre-charge.
That depends on P. Yes, absolutely, you're right. That depends on the value of P. You can select the value of P such that if you do that, you'll lose. But I agree, yes. If it's really, this is a very good point. That's why there needs to be more work in this area. What is the relationship of the P such that P doesn't need, that doesn't need to be random?
Even if you use a count of carrying which row, note that the memory controller can access the post so many times between refreshes.
Uh-huh.
Doesn't matter which. The worst case, it accesses the same row.
Uh-huh.
If you guarantee that you go and do this enable every, let's say, 500 times, and it needs 510, and even in the worst case you won't hit, there's no way that if you sneak 500 to the same,
Yes,
it's like a finite budget.
exactly. It's a finite budget, basically.
Conversation formulas.
Exactly.
If I guarantee that, tell me how many you can do, if once in that many have that, I do activate, then I think there's no way you can hit me.
Exactly. So basically, but I think
Deterministic symbol doesn't care about the full
I agree with you, but that depends on the value of P. You need to select P very carefully such that you don't need to be random. But we can take it offline. Okay, so I'm going to finish with something because we're running out of time, I think. This is something for fun. I don't know if this is really real or not, but this is what I saw in one of the blog posts on one of the, I guess, Lenovo's. Basically, this is the BIOS. You have hardware RowHammer protection versus 2x refresh. I don't know if this is true. You can choose between it. And if you look at this is the RowHammer activation probability that you can choose. Is it over there? Do you know what it does? Okay, so maybe you could. Okay, there you go. Exactly. Yeah. now it's confirmed it's real. I have to come to Israel to confirm that it's real. So basically, yeah, there's activation probability in real life, as you can see over here. So now I'm curious about that activation probability. We'll discuss this right after the lecture. Okay, so this is the paper, and this is the other paper. I think, yeah, as I've discussed this earlier before, but these sort of scaling problems are important. The solution, I think, a good solution is really what's also proposed in this paper, co-architecting controllers and DRAM such that you can enhance the DRAM process scaling. And the solution that we propose for RowHammer is essentially doing something very similar to this, system memory co-design. So basically, we want more intelligent memory controllers. We're going to talk more about flash memory at some point, but flash memory has a lot of mechanisms that are much, much more sophisticated than what we just discussed. There's a lot of interesting stuff in here. Actually, read disturb errors, we've studied the read disturb errors for a long time in flash memory. It's in some of these papers over here. They're very well known, and preventing them is important in flash memory also. That could also lead to security vulnerabilities. And as I said, this is something that I would recommend, but this is not something that I require because it's actually a long paper. It's about 40 pages or so, I think. But a key takeaway, I think, from RowHammer is we want more intelligent memory controllers. Actually, if we had a slightly patchable or programmable memory controller, you didn't need to do any of this refresh or anything, right? You could actually fix this in the memory controller without worrying about increasing the refresh rate significantly. So going into the future, a more secure design would be making the memory controller more patchable, slightly more intelligent, more programmable, such that if these things appear in the field, okay, maybe we can actually sneak in some microcode in the memory controller that does this refresh or maintenance, right? So this brings us to more fundamentally secure, reliable, and safe architectures, and that's what I'm going to start with tomorrow, since we're out of time right now. Does that sound good? Okay. Okay, I'll see you tomorrow then.